Hello, and welcome to the third in our series of videos on 3D graphics in Qt6. I'm James Turner, one of the 3D developers at KDAB. Today I want to talk to you about how changes in the rendering and hardware graphics APIs offered by different platforms has driven evolution in how Qt6 talks to the hardware and the changes that means for you as a software developer. Let's start by looking at the challenge we face when talking to graphics hardware, and therefore why we need rendering APIs to solve this problem. A rendering API, or graphics API, or hardware acceleration API, all these names have been used down the years, is some way to talk to specialized hardware which makes graphics rendering faster. This has been the case for a very long time, almost since the beginning of computer graphics. There's been small or increasingly large bits of silicon which can do work around graphics, maybe as simple as copying 2D areas, but obviously increasingly doing full 3D rendering. Whenever we have hardware, we need an API for user space programs to talk to it. And unlike other areas where we have specialized hardware, maybe input devices, storage network devices, the range of features offered by graphic acceleration is much more variable and has continued to grow continuously year on year. Whereas the feature set offered by, for example, a network card or storage device, while it has evolved, has remained relatively slowly changing in a very gradual way over the same time frame. To start with, let's look at some history of how hardware graphics APIs have evolved. The first general purpose graphics API was OpenGL 1.0, which actually came from Iris GL, the graphics API specific to silicon graphics machines. OpenGL was a generalization of this to be a neutral API tailored around 3D graphics, which is supported by different industrial graphics card vendors. In parallel to this, from especially the PC world and also console and 16-bit machines, were a series of APIs around 2D acceleration, some of which were exposed to, for example, GDI on Windows or X11 on Unix systems, for example, the XAA, which is the X acceleration architecture. These typically had limited APIs to accelerate copying 2D areas, sprites, or text rendering, as was needed in 2D interfaces of the 1980s and 90s. In parallel to this, we have the launch in the early 2000s of consumer 3D graphics hardware, principally driven around gaming, and the Microsoft Direct 3D APIs, which were launched more or less in tandem with this and evolving at the same time. Again, driven by the games market, consumer graphics cards added more and more features, starting with texturing, then multiple texturing, then different blending and compositing operations, and hardware lighting support. Each of these steps meant more APIs being added to D3D and OpenGL to cover the new features with extensions, new versions of the API, and more complexity in the usage to take the best possible advantage of these hardware features. While this growth was ongoing and quite rapid, there was a major shift in the use of the APIs when hardware became fully programmable. Suddenly, we no longer need to specify every detail of what the hardware is doing through the API, but rather we're going to pass it some bytecode or even C-like code in, for example, maybe GLSL or HLSL, which is then going to be compiled by the driver and run on the hardware. This change to programmable APIs meant a huge amount of new API, but also that many existing pieces became completely obsolete. One important feature of these newer graphics cards and the large amount of memory they have is that there's a large amount of data to be managed. Textures became larger, buffers, and even vertex data. Each of these might now be tens or hundreds of megabytes and need to be efficiently shared, managed, locked, copied, or ideally not copied when talking about them from CPU or GPU side access. So memory management, resource management start to become very important parts of the graphics APIs. Of course, we also want to run our CPU and GPU code in parallel to get as much performance. And we also have the arrival of general purpose 3D engines such as Unity and Unreal, which want to tailor every single aspect of the graphics behavior to fit their needs and their knowledge of the scenes they're displaying, the maps they're loading, unloading, and when items and resources might be needed. They want a lot of very fine-grained control, and particularly some older APIs tended to try and hide these details of resource management, whereas the modern engines want to have that control exposed to them so they can make very intelligent and accurate decisions. So that's the general situation. Now we think about Qt specifically. Qt6 1.0 was launched in the Qt4 era and was built on QGraphics View and QPainter, which are themselves primarily software-based APIs. There are some ways to use QPainter which can offer hardware acceleration, but principally when we talk about using QPainter, we mean CPU-based drawing. For the Qt5 era, Qt6 was rewritten as Qt6 2.0, which is the main version we think of. And this was built on the assumption that some form of OpenGL, either OpenGL itself or the embedded version, would be available ubiquitously on all supported platforms which are targeted by Qt5, including Android, macOS, Windows, and Linux. Of course, there was an awareness that the OpenGL driver situation on Windows was often a bit lacking, but fortunately there's a solution to this problem. There's the Angle library, which is part of the Chromium project, which gives you a OpenGL ES2 implementation running on top of D3D9. And therefore this gives a solution to the one problematic platform as it was seen, Windows, to therefore have ubiquitous OpenGL on all the platforms Qt needed to target. This choice to base the Qt6 rendering layer on top of OpenGL means that OpenGL concepts appear directly in the Qt6 API. For example, we're talking about textures via an ID number. There was also recognition that there would be some platforms and hardware running Qt5 that might not have OpenGL support, and therefore there was also support for a software renderer with reduced features, but which could do smaller screens and simpler graphical content without needing a hardware GPU. To see how this picture has evolved in Qt5 and then into Qt6, you talk about the scene graph abstraction, which Qt6 uses to separate the high-level concepts you work with from the low-level graphics API. In between is the scene graph. What is a scene graph? Well, it's a very standard technique for organizing rendering, where you have a hierarchy of nodes, technically a graph, as the name suggests, but in practice nearly always a tree. Higher levels in the tree will deal with transformations and clipping, and lower levels in the tree will typically specify a number of vertices or triangles to be drawn, making up maybe a rectangle, a rounded rectangle, a piece of text, or something more complicated. Crucially, materials can be used to assign the appearance of drawn elements, and these typically will involve using shaders to, for example, simply do a flat color, some transparency, or a gradient. And textures can be used to give images visible on the screen. Everything you see on the screen in Qt6 is basically drawn by doing some combination of these triangles, rectangles, with textures applied, with shaders applied to give you anti-alias text, to give you moving video, to give you gradients, and so forth. An important feature of the scene graph is it's extensible. The scene graph API is public, and if you need to, you can add in custom drawing nodes and rendering nodes. You have examples of this both shipping with Qt and also on the KDAB website. If you need to do a very efficient shape or a very large number of custom shapes, then making a custom scene graph node can be the right solution. And when you do this, you're working with the scene graph API where you specify shaders, vertices, and that kind of data. This is a lower level API, but it is a public API, not a private one in the Qt sense, so it's stable between different versions of the Qt5 series. So that was the situation roughly when Qt5 launched or in the first few versions. But as time went on, it became clear there was a need to support other kinds of rendering backend, particularly a D3D backend. And so this drove some changes in the API that had to be done in a compatible way, again, remembering that the scene graph APIs are semi-public. This meant that there's actually a series of backends available now, depending on the license of Qt you're using, and depending on which scene graph backend is in use, for example, the software renderer or the D3D renderer, then certain features might not be available. For example, the Qt graphical effects module relies on OpenGL or GLSL shaders, and the shader effect system, again, by default assumes a GLSL shader. If you're using a different backend, actually you need to specify these as HLSL shaders, which are similar, but they're not compatible. So essentially, when you use a different backend, you have to be aware of the differences and probably have some if-defs in your code or different files loaded to ensure that you get the same rendering result you want. And certain modules, for example, particles or certain kind of text rendering, may not be available in the chosen backend. But of course, the core features of Qt6, items, images, rectangles, usually will work exactly as you would need to. During the lifetime of Qt5, the rest of the world was moving on. The big changes are that Apple launched the Metal APIs as a replacement for OpenGL on its platforms, and the Kronos Group launched Vulkan as a alternative to OpenGL on Windows, Linux, and other platforms there. Metal and Vulkan are complemented by a new set of D3D APIs, and all three of these systems are essentially very similar and offer a new and lower level approach to accessing the hardware. Coupled with this, while many embedded platforms do support OpenGL much better than they did when Qt5 was launched, it's still the case that because an OpenGL driver is a very large, complex piece of code, in some cases larger than a kernel, the quality of OpenGL drivers has not improved consistently on different embedded platforms, and even newly launching embedded platforms don't necessarily ship with perfectly working OpenGL drivers, even in contemporary times. So what can we say about these new APIs? Well, essentially they all offer better performance and more fine-grained control over the hardware resources, but the trade-off of much increased complexity for the developer. In OpenGL, you can establish some rendering with maybe 30 or 40 or 100 lines of code. For something like Metal or Vulkan, you're probably talking more like 500 or 1,000 lines of code to get anything rendering on the screen. It's a much lower level, more powerful API, but a lot more work to be done by you, the developer. The good news is all the APIs are basically very similar. They all embody the same concepts with some differences, but unfortunately, although they are similar APIs, they're not identical APIs, and that means there has to be some code that's aware of the differences and makes that work. That brings us very nicely to talk about the rendering hardware interface, which is the part of Qt6, which abstracts these different hardware APIs into a single API that Qt can target and use for 2D and 3D rendering. What does RHI do then? Well, it abstracts Metal, Vulkan, D3D, potentially other APIs in a single API that higher levels, such as the Qt Quick scene graph, can work with. It gives features to support the 2D rendering you did in Qt Quick, but also in Qt Quick 3D and Qt 3D. It does not targeting particularly 2D or 3D, it's simply exposing the features that the rendering hardware can support. It defines generic types for various standard concepts, such as a buffer, a texture, and other kinds of resources. And then also for the rendering things, so things such as a pass and a pipeline, which need to be assembled and configured in all of these APIs before drawing can happen. It gives a way to actually issue drawing commands so that you can see things on the screen once you've collected a certain number of drawing commands together. And finally, it gives explicit resource management APIs, so you can say that a collection of resources should be uploaded, downloaded, or copied at a particular time or in the next time that these transfers are occurring. Taken together, these are all the building blocks we need to build up an actual functioning rendering engine on top of an arbitrary graphics API. There's a few details which are worth mentioning. Technically, RHI was available as a tech preview in Qt 5.14, and it is available as a supported backend for Qt Quick in 5.15. But we're mostly considering here the version in Qt6, which has evolved somewhat from those early versions. Notably, RHI is the default rendering backend in Qt6. RHI is a private API, so there's a QRHI header, but it's an _p header. This means that if you use it, you're not complying with the binary compatibility guarantees of Qt, and therefore when you upgrade from, say, 6.2 to 6.4, you could get some breakage. As with all private APIs in Qt, it's unlikely, but it's absolutely possible, and if you want to have the binary compatibility, you cannot use the RHI header in your code. Aside from the main RHI header, there are also integration headers for each of the different backends, such as Metal or Vulkan. This means you have existing code which, for example, produces decoded video as a Metal texture, or decoded surfaces from a vision system as Vulkan textures. You can then integrate these directly into the RHI layer. So there's bridging code, which is obviously used in different extensions of parts of Qt to make efficient integrations with the native APIs on different platforms. One important area to focus on is shader handling. Each of the hardware APIs has a slightly different shader format. To make this work, there is some additional tooling which happens in Qt6. Essentially, you write your shaders in a neutral shader format, which is GLSL. This is translated into SPIR-V by the GL slang compiler. And then the QSB tool, which runs at build time or deployment time, creates versions of this for each backend that might be used. So you then typically ship these QSB Qt shader binary files with your application. And when, for example, the Qt Quick scene graph needs to load a shader into a material, it will find the QSB file and select the appropriate shader bytecode, whether it's running on Metal, D3D, Vulkan, or something else. It's worth pointing out this is an area where there's already some flexibility. The approach I just mentioned is used by Qt Quick. In Qt Quick 3D, a different approach is taken because there needs to be more assembly of shaders. So you may remember from our discussion of Qt Quick 3D that when you supply custom shaders, they're actually fragments. They're assembled into a larger shader, then gets compiled. The approach taken in Qt Quick 3D is to use GLSL for all of this and then translate that at runtime into the required shader, for example, HLSL or for metal and so forth. Let's talk about some of the implications of this RHI layer and then where it leads us in terms of 3D development inside Qt6. If we want to run on all Qt6 targets, we have to use something that supports all the different rendering backends that RHI itself might be using. It's worth pointing out, of course, that OpenGL does still work on the vast majority of targets. So as a migration strategy, using OpenGL is a reasonable approach. It will just eliminate some platforms, but it can be made to work in the vast majority because OpenGL, even on Apple platforms, is only deprecated, but it still does exist and run. It may not run forever, but it runs a bit. So where does this leave us? Well, if we want to run on Qt6, we support the different hardware interfaces that it itself supports, whether that be Vulkan or Metal or something else. However, OpenGL is very widely supported. It runs on nearly all these platforms in some form or another. So as a migration strategy or as an initial way to get things proof of concept, OpenGL is still a reasonable way to proceed. If you're targeting a particular vertical market, such as a Linux embedded system, then it's completely reasonable to tell Qt6 and RHI to use one backend, such as Vulkan. You can then write all your code knowing the backend in use will be Vulkan and find an appropriate engine or API to integrate with that. In the general case of a 3D renderer, you would need to find a renderer which can target those different backends we talked about. But there is another option which we've used successfully on some projects, and that's to port a 3D engine to use RHI as its rendering backend. The API provided by RHI is again very similar to what's offered by Vulkan, Metal, and so forth. This means that generic rendering code can be made to work using RHI as its abstraction, and then it will of course be automatically using the same internal hardware abstraction as Qt6 and other parts of Qt using. This gives a very seamless integration at the cost of rewriting some 3D code to use the RHI abstraction. Of course, the RHI interfaces are private. By doing this, you will not be binary compatible with different versions of Qt releases, but this is maybe an acceptable trade-off for the other benefits it might give you. In conclusion, this gives us three main approaches for doing 3D content inside Qt with the RHI layer. The easy one, of course, is to use one of the integrated solutions we talked about in the previous video, which automatically use RHI, and therefore 3D content and 2D content are aligned and will work using the most optimal API for the platform you're using. The second choice is to have 3D rendering code which uses its own interface to the hardware and ensure that this aligns with Qt. For example, using Metal if Qt6 is using Metal. But especially this can work in certain markets by restricting RHI to picking one or a subset of backends and ensuring that your rendering code uses the same ones. Again, this might be as simple as saying we use OpenGL or we use Vulkan and then eliminating all choice from the possibilities. The final interesting approach is to adapt existing general purpose rendering code to use RHI as its rendering abstraction. This is essentially what Qt 3D and Qt 3D both do. And because those engines already target the RHI layer, it has all the features you should likely need in your 3D code to again target these abstractions in a generic way and still get your rendering performed in an efficient fashion. Thank you for taking the time to look through this rather acronym heavy set of information around Qt6 and the different rendering faces. I hope it was useful understanding how all these pieces fit together to give us performant graphics in the Qt6 era.